Hey, good morning everyone. Please let me know in the chat that you can hear me well. Okay, we'll not try to scream in microphone so loud. So anyway, so can you hear and see well? Plus, minus, and then we'll start. I have also some nice things going on in regards to previous works that we did in this course, where unfortunately we did not see at the live session that the results were super good in the plots. I mean, like the accuracy plots were good. Accuracy plots were good, but the like scatter plots were not good. And then I found out what was the reason actually for that, and it's very interesting how I actually found it, because I was starting to use also TensorBoard, and today we'll try also a really nice way to display metrics using the not metrics but embeddings using the TensorBoard. There's a really nice way to do that, and yeah, when I started projecting in TensorBoard, I see everything is fine, but then in the plots, everything is not fine. And then I was thinking how it would happen, and then I found the really strange kind of matplotlib issue, which I will also share to you as well. Okay, sorry, I have some, just a second. Sorry, yeah, I had one interruption here. Anyways, so yeah, we'll show you that part as well. I really got I think quite good results with regards to that as well. So let's first start then looking at some of the things with this bug. So I also posted the bug in the Google Classroom. So here in this line there is a bug fix. So this is really super strange bug, because the matplotlib, if I do the show function down here, there is a show function, right? So if I do the show function, then all of my line plots, which are, I don't know, there's image plot, there is a line plot, right? All of them gets refreshed, but for some strange reason, the scatter plot is not refreshed. So every time when I do the next epoch, the previous epoch points stay on the plot, and that's why we got like some kind of super strange results where nothing is clustered or it's wrongly clustered. So, and then I was trying to desperately do all sorts of ways to improve it, but it did not improve. So the only way how to improve it was just to add this small one line. So before every epoch, clean the plot, and then the scatter plot would start behaving normally, because otherwise the scatter plot is just behaving like totally wrong. So that's I also updated the homework templates, by the way, and today we're going to work with proper version. But that's just one of the reasons why. Basically, that's one main reason why the kind of results were not as good as I was expecting visually. Just a second, I will also take a quick look and share on the Jamboard now the results with this line. So if I just enable that, like this silly line, right? What will be the result on the contrastive loss with some kind of mining operation? It's also without mining operation you will get better results there. So just a second. I ran a few experiments yesterday just to confirm that this is working. So let me see. So I even did not manage to look fully at the experiments, but it seems that it should be good. So okay, I will just take one randomly. So from 99 epoch from contrastive loss, hopefully it will load up for me. I don't know what, something is not loading. Okay, now it's loading. Really strange stuff. Anyway, okay, so let's go to my on the Jamboard. The Jamboard slide number Slide number 2. And again, today we're going to look at the tensor board methods, where you have even nicer ways to display the results. But these results at least show some encouraging signs, anyways. So here, what we see here is that the train accuracy basically increased, and then test accuracy, which is the orange line, it also increased. Actually, the best test accuracy was somewhere in the beginning, and then it started overfitting quite fast, actually. So, okay, let me take another example. I will take about like from 15th epoch, because it is already, I see that it's overfitted. So let me take something which is not overfitted. 15 epoch, let's say this one. Okay, so this should be, yeah, this is much better. And actually it was really interesting to see what overfit means in the terms of triplet loss, which is really, not triplet loss, but contrastive loss, which is really also really interesting. So I will share that as well, actually. So this is before overfit, and this is after overfit. And again, the only thing that I changed basically is just to that plot line. So before we saw only the charts, we didn't see proper scatter plots. So here you see really nicely. So this is just the linear PCA. I hope that it was linear PCA. So, but basically, every class is clustered in some manner. There are some splittings happening as well, probably because there is like something interesting in dataset. I mean, like some letter is in one way and then another way, and then they start to split a little bit. Or it also could be an artifact just from the dimension reduction as well. So that is after epoch 15, and we also see the test plot, which is really interesting, because test plot, these samples, the number 3, the A letter, the number 6, all of these small guys here, they were not seen by the model. So these are completely new data classes, and basically they are. You can see very clearly that they are also clustered together, and there's also some kind of like 3 and 6 which are similar, right? So they are together, and then G and 6 is also together. And then A is more on the bottom part. So that's really interesting. So that is before the overfitting, and this is after the overfitting. After overfitting, you see this effect. This effect is really, really something that you could avoid by applying constraints. Like, for example, do not feed in model something which is already well clustered. Only feed semi-hard samples, or basically, yeah, or hard samples, but never feed like any easy samples. Otherwise, it's collapsing down to one point, and when it's collapsed down to one point, then also the test plot seems really, really messy. So this is before overfitting, and this is after overfitting. And you see that their mode collapse happened, and all of the embeddings just collapsed to the one point. Basically, this is also the similar stuff what happens in GANs, generative adversarial networks, when the mode collapse happens. So, and yeah, so this is a really nice way to show the overfitting in the deep metric learning. So again, just to repeat you, maybe I should drop in the line in the slides, that there was this nasty bug with the scatter plot, which I did not know exist in the matplotlib, that basically if you don't clear the scatter plot, it doesn't clear itself. So probably useful information to know yourself for your own project. I don't know, like this is really strange, but yeah, this is what happened. Okay, let's move on. So I hope this is interesting and cool to see that this actually worked. Yeah, last time it also worked. It gave you the accuracy plots, but it didn't give you these nice scatter plots. So now it's working. Anyway, so let's move to the triplet loss then. Okay, it's actually on the first slide as well. So yeah, there is a LeCun and Andrew Ng, two AI scientists which are really important in deep learning. So from Stanford and New York University. Anyway, so remember that in the in the CME's networks, in the contrastive loss, we only had two pairs, right? But in the triplet loss, the idea was, it actually comes from the paper, FaceNet paper, so triplet loss primarily, I think maybe there was some ideas before that, but it comes from FaceNet. I think it was 2015, if I'm not wrong. So basically, and then they added additional one element, so it's a triplet, basically two positive pairs. So this is two positive samples. These are the same, and one negative. So I mean, one is anchor. So the middle one is an anchor, like anchors. Yeah, the middle one is anchor, and then there is a positive sample, and then there is a negative sample, and every time when you call loss function, in the loss function you would have all three terms. So it means that it will never kind of go towards one direction, so basically with a contrastive loss it might be possible that you are like trying to avoid one class and run into another class and then collapse down to yourself. So that it's a lot less stable than the triplet loss, but later we will see that there are even more stable functions than that. So that is the main idea, but then the loss function itself and also some visualizations. Let me pull up those for you. So just a second. How can I see them as pictures? Like that, probably. Oop. Yeah, sorry for a little bit messy stuff, but we'll catch up. So this picture we had. Again, let's use this one to show in the space how it looks like. Again, by the way, the FaceNet paper was specifically for face rate identification task, which is also like the zero-shot task, or it could be also end-shot task. Remember, the zero-shot and end-shot is different by or K-shot is different by the way that in the training set we include few samples from the test set, or we don't include any samples. So again, in the embedding space, we try to get the same pairs together, the different pairs further away. So that's the main idea here. And then the loss function itself looks like this, and we will need to think about it a little bit more. So, oh no, I don't want to do that. I think this is from the FaceNet paper, if I remember correctly. So that is the loss function. Visually, if we would use the cosine or cosine similarity, cosine distance, or some like cosine angles, then we would have something like this as well. Basically, the idea okay, it's not actually cosine angles, but anyways, so the idea is that I want to make positives closer, negatives further away, but it could be also as an angles. Again, just to remind you, if you have high dimensional space, like if you have embeddings of 256 dimensions, by the way, the larger embeddings, it doesn't mean that it will be better. Like all of the embeddings mainly converge, like so in around like 32 till 128 dimensions. This is optimal size, because after that size, the kind of like all of the random distances will just become equal. Basically, that is what actually you want, but it doesn't matter. Like if you have only 512 dimensions and all of them are at equal distance at the very beginning, and they are also at equal distance at 64 dimensions, then it kind of doesn't make sense that to just add more dimensions, add more confusion, add more like kind of like randomness to your embeddings. So you actually want to have the smallest possible embedding that captures the most kind of most important information, semantic information, so that you could use it properly on on production, right? And even if you get like 0.5% more on some kind of test validation set by adding few hundreds of extra dimensions, it will not help in production at all. It will just make a lot more problems. And in case, so if you have 32 dimensions, then you would use probably Euclidean distances. And if you have like 128 plus, then you would use probably cosine distances. So because they would have larger difference between the vectors than Euclidean. So that's just from the math side. I also have some plots for that if you're interested, but right now I don't want to just like focus more on the things we need to do. So here the loss function. The loss function, this strange term, right? I already explained, I think, this once. So this strange mathematical notion, basically with the underscore plus, it means the same as ReLU, or basically it means also the same as as ReLU. Let's write it different way, like that, or it means the same as the max 0, x. So basically all of that is exactly the same stuff. Like I don't know why somebody just invented these kind of notations. By the way, there also is that something not really nice in this equation, because normally in LaTeX you have these square brackets. You have, like, if it's a max function, then the top part should not be here. Should be just like straight line, and then the bottom part just like that. But it is there, so basically this is not super cool, but basically this is the way how it's written. So anyway, here we have the anchor. So the F is the model, right? So again, it's a convolutional encoder, or any, like if you have like time series, if you have any other types of data, you can have different kinds of models, right? And it generates this embedding, so the model for the anchor, and then for the positive pair to the anchor. By the way, you definitely also think in the FaceNet paper they invented the semi-hard method for triplet loss. So it means that you would select samples which are only in the semi-hard area of the space, but you could also select the hardest sample. You definitely don't want to select the easiest sample here, so otherwise it will just collapse to the zero, like just towards 1 point, like we saw in the previous slide where there was this mode collapse happening. So that's why it's very important, again, which samples do we choose here, and also the same for the negatives. And then there is a plus the margin. So again, the same idea is that we want to keep all of the clusters with some margin apart. So again, the idea is that we have one cluster here, we have another cluster here, and there's many other clusters, and between the clusters we have this alpha margin, and the clusters are floating in the embedding space all the time while you are training. And if you also apply this semi-hard constraint, then also a nice thing is that it's very hard, I think, to overfit actually this model, because then you would never actually get any like kind of easy samples, and this thing would actually never happen if you would apply a semi-hard constraint. So I will show you just in a second, again, just to remind you what was the semi-hard constraint. So, copying this thing. Hopefully I can put it somewhere. Okay, let's make it smaller maybe. Anyway. Yep, so we have the anchor, we have the positive, we have the triangle negative. So if we just include, so the hard samples, the most hard sample would be the closest one, but we could also include not only the closest ones, but also those which are at all in this area of hard, which means that basically the further away, like the radius is defined by probably, so yeah, you see by the alpha here, And I guess the semi-hard area is defined by the alpha minus sample detected here on the boundary. So anyways, there are some ways how you can like filter out which samples you want to feed in here. Again, the main reason why you want to filter out at all is that you want to avoid situation that that they collapse to just one point. So, or if you don't filter out, you can live with this, right, and just early stop and then save the date, save your model at some point of the time. In practice, it's better that the clusters float around in the space. So it's better that the clusters are floating all the time, that they are not just find their balance, the equilibrium at once, and then just stop. And now let's before starting coding it, I already shared the template, by the way. So let's think about it a little bit more. So max 0, so either max 0, then we have some distances, distance positive, plus, minus distance negative plus alpha, right? So this would be the loss function. Oh no, okay, yeah, so here. Now if we choose alpha 0.2, which is like common margin, because like in L2 space, the maximum is 2, the minimum is 0, right? In cosine space also, cosine distance space. In the cosine similarity space, it would not be the case. It would be -1 to 1, and then this function would probably not work very well. Because it definitely will not work very well, because it's not designed for something where the distance metric is in minus. So definitely L2 distance or Euclidean, or the cosine distance, or anything that that means that 0 is the closest one, right? So that is that area. Then let's model some cases. So to get the loss function as 0, right? Then it means that what we need to do is that did I write it correctly? Just let me check. I hope I wrote it correctly, yeah. Yeah, I think I wrote it correctly. So anyway, so yeah, so then we would need to have the so this would be then 0.2. So it means that all of the positive samples would be like in some kind of cluster which radius is about like 0.2. So it doesn't guarantee that they will not collapse to one point, which is not great, but basically but we can control that by constraints anyway. So that's one part, and then the other one will be minus 0.4, for example, one of the combinations. That would be just one of the combinations. It could also be, you know, like there could be also some other combinations which would not mean that the cluster is that dense, you know. Basically what it means that the cluster can be also larger. So this means that this is a larger positive cluster. And this is good because it allows the model to learn themselves what is the variance or standard deviation of the cluster. So it means that maybe some person face is have like pictures which are like with some crazy outfits, and then it's harder to classify them. And then there is another set of pictures which are very similar, which have like a smaller positive cluster, right? Smaller positive cluster. So that's one. Then also, again, it doesn't guarantee that it will not collapse. So, but basically, it's really nice loss function from one sense. We also need to ensure that we always have like anchor, positive pair, and the negative, right? And also we want to have that it's not randomly just any positive pair. We want to have some choice. We want to have that we can choose from two anchor. I mean, if I have the anchor here, I want to choose some other positive sample. I just don't want to take the first positive sample that I have. So we should have some built-in strategy to try to choose which sample we should use for the positive pair. Okay, so I understand that there's quite a lot of things going on around here, but let me ask in the chat, is it clear so far? Plus, minus, and what can I explain more if it's something is not clear in the chat, and then we will move on with the coding. And thank you, Kristaps, for answer. I really also happy to see Matis. He's also a really smart guy. So he will also definitely help me out if I have a bug. So really thank you. Grateful that you're joining, and hopefully others who need to join, who need to get marked for this course will also watch and interact. So anyway, let's then move to the code. Again, this session and then the next session will be more on the deep metric learning, and then we will move to the generative models. That will be really also exciting stuff. Oh no, I just realized, oh no, that is different. No, yeah, this is good. So it might be that in your template I accidentally left the include TensorBoard X, import TensorBoard X. If I did that, then you can just comment out or delete that line, or you can install here in the bottom part in terminal pip3 install pip3 install TensorBoard X, but we will do that a little bit later. So you basically, if you later need to install the TensorFlow and TensorBoard X, just because to show there is a really nice tool that we can use to visualize embeddings. We'll do that a little bit later. So here in the code which I made, there is nothing that, yeah, there is this guy. I forgot about him. Yeah. Okay, let's do then the TensorBoard stuff now. So we need to import TensorBoard X, no, from TensorBoard X. I will drop this also to Jamboard so you know. Import summary writer. So if you don't have that line, please add that. And to install it, basically you need to call it pip3 install TensorBoard X. I hope that this was the command. We will not use it immediately now, but like I just realized that unfortunately I have left some lines from the TensorBoard stuff. I don't want to cause some errors here. So yeah, it works. Great. So I'm dropping this line inside the Jamboard as well. And yeah, while you are at it, right, on the slide number 5, you can install also pip3 install. Whoa, interesting. Say you don't have template. How that's possible? Template 3.2 triplet loss template. Why do you need 3.3? Oh, you saw my code, right? Anyways, I just renamed my code like that. Don't worry, you're very careful of seeing numbers, so that's great. But basically, your template is the same template as my template. Anyways, I will actually update maybe the one that that you're referencing to. Where was it? Here. I just before the session deleted this stuff, but it should be there. Anyway, then also install please pip3 install TensorFlow if you don't have it. TensorFlow. We will use it only for visualization. TensorFlow. Like that, right? Do that as well, please. You could install also from Conda, but at least if you would like to use GPU, then definitely install from Conda. But as I don't want to use GPU, then I install like that. Okay, so I will update the template also for others later. Okay, I will do that a little bit later. So really nicely that you can see even that small details. Crazy. Anyway, so that's good. That's good. So okay, install those things. But while it's installing, we can start looking at working and other things. So here, why I asked you to install, because I already added the TensorBoard summary writer here on this line, which means that there is a specific tool, basically class, which allows you to write all sorts of metrics inside the TensorBoard. And here also there is one commented out to add how to add the scalar values to the TensorBoard. Okay, this seems really strange stuff. Did I share you this template? Okay, I think I added, so I left some stuff down here, right? Okay, so you're lucky. you will not need to write yourself a lot of stuff with the TensorBoard. Anyways, but I will write it step by step anyways, just to make sure that we have everything as we need. Yeah, that was really fail. Did not see. Let me check. Did I left something more? Oh no, to do. Okay, so good. Good. Just the TensorBoard stuff was left there. Everything else was there already correctly. So compress. Okay. I will actually update this to the server. Just don't want to make sure that we have everything right. Okay, and then I will use this one. Right. Okay, cool. So then we have the same code as previous time. The emNIST extended NIST letters, right? There are lots of digits and letters and numbers and all sorts of written letters, right? So that dataset we have, it's a grayscale dataset where there's the dimensions are 1, 28, 28 pictures, right? Small pictures. Then we have some these hyperparameters, which mean that like what kind of how many classes do we want to include, how many labels do we want to include, right? Then I'm creating a chase, so cache. So basically the idea is that in a pickle I'm saving the indexes for the train and test dataset. So I don't want to do the splitting dataset every time when I run the script. So this is a little bit of piece of code which might be confusing, but basically I just wanted to add everything at one file, so let's leave it as that. It's just the idea that I want to select classes. So if I say that I want to include maximum number of this number of classes, right? Then for each of those number of classes I want to include maximum number of samples, right? And then I'm just selecting out all sorts of indexes from the dataset, collecting them as lists, and then I'm using really nice torch tools, which are subset, where I can select all the indexes from the dataset pool and use it just as my own dataset. There is also, if you wonder, there's also really other nice tools in the Torch data. What else? Like, for example, concat dataset. This one is super useful as well. So you can concat many datasets together and use them as a one dataset object. So also the same idea, using just the indexes, right? So then there is the one new thing which we will code now, is that I added my own data loader triplet. So this is a batch generating code. I replaced the data loader from PyTorch with this one. So we would generate, so the idea for this guy is that we want to generate every time when I call next, I'm generating X and Y. And by the way, this structure is also really nice. You should, if you don't know how to write in Python iterators, you should definitely look at this code and think about it. So the idea is that when I'm calling for each, every time when I call for each in this kind of object of data loader triplet something, then this function gets called, like every iteration. But every time when I enter this kind of scope, so let me actually write it step by step. So every iteration, this is called, and on every time when I enter, every enter we'll call this. If you know that there is also operator for with function, then also there is a enter type of function. So basically you reset the counter and then you go every iteration, and then when you reach the end of your like batches, then you raise the exception, stop iteration, and it will go out of the for loop. So this is really nice structure. Then also the length is necessary. You could also not return length, but because iterators means that this is actually iterator pattern as well, design pattern. So it means that you could have like loading from database forever something, right? Without the end, like you can load some kind of like generate some samples forever. So, but in this case we're using length because I want to use the TQDM loader bar knows how many samples we have. And then here they're just stacking them together. And now I just want to explain what is expected output. So the expected output for y's, I want following. So if I have y indexes, so these are the indexes actually, right? So the class indexes. I want that they will be in this manner. So I have the class indexes, let's say 5, 5, 5, then 7, 7, 7, then let's say 10, 10, 10, and so on, till the batch size. So idea here is following. I will choose as an anchor first in the triplet here, and then I will choose which one is better sample, either this or this to use for my triplet loss. Then I will select the negative sample from all of the rest of the samples after the first 3 samples, right? So that's the idea here. And of course we could add more samples. So it might be probably even a more powerful way of kind of like mining samples if I'm just adding like by 4 samples here, and then choosing better samples from 4. Like if you want, you can change the code in that manner as well. It's just that it's not good if it would be just by 2 samples. If I'm doing like this, it's not good because this will be just completely random choice. They're like every time the pair will be, it might be good, it might be bad, right? That's one. There also if I don't have at all any kind of batching operation, if I'm just having everything like this, and if I have a lot of classes and small batch sizes, then definitely I will not be able to use triplet loss at all, because for the triplet loss I need 2 of the same. If there is no 2 of the same, it will not work. The contrastive loss in turn, if I have not 2 of the same, I can still execute half of the loss function, right? for the triplet loss, I cannot execute just half of the loss function. It's just all at once. So that's why we still need to have some kind of procedure to generate proper batches. So that's why we're having this part. So we're having this part, right? So let's then code the batch generation code. Again, I will try to write it as short as possible. It will not be probably super optimal as well. So definitely, if you know a better way how to write it, I would be really happy to see. So if you submit in some better way and let me know, I'll be really happy. So let's see. So we'll have similar way as in some kind of search algorithms, right? So indexes free. So free indexes will be np np random permutate. So permutations, it would be, I'll just write it and then I will explain. So len self dataset to list. I will write basically also how you can write the same line another way. So permutations are just a random order of some sample set. So you could rewrite exactly the same stuff in the following way. So let me try to show you. Random shuffle np range. Oh no, I think it was like that, to list. So basically this is the same stuff. Maybe some typo, but basically this the same logic as in the above line. I'm just showing like what it is, right? It's just generating the list of the indexes and then shuffling them around. So that is a permutation. So that part. Then so these are the indexes free. Let's get also labels free. So there is again so many small details to this code. So if I'm just like ignoring the labels, then I can unfortunately get a situation where my batch looks something like this. So the y's looks something like this. So 1 1 1, then 2 2 2, then 1 1 1, and for example again 1 1 1. So I don't want this kind of situation. This kind of situation just means that the batch is totally imbalanced. There's like just from one class more sample triplets than from other class. So I want to try to, as much as possible, to include variation of triplets there, or variation of choices, because these are actually not really the triplets, they're just choices. So that's one of the things. So I will use labels to capture, like, so that I have always the kind of all of the labels in order, right? So self labels. So this notation with list means that I'm copying the list pointer. I'm not copying the list pointer, I'm copying the list, and the pointers inside the list stays the same in both lists, just the list object is copied. So that's just a list, yeah, basically is reconstructed. So I mean, if I'm now modifying the labels free, it will not modify this one. But if I modify samples inside the list labels free, then it would be also modified in labels y. Again, this is something that I'm especially focusing also in the beginners courses, that like sometimes students still do not get that in Python everything is pointers, and you can easily mess up something if you don't understand that nothing is copied automatically. So from the complex objects. So ID access. So these will be used samples. And then we will also have IDX label. So this will be the current label in our batch. So what I mean, so we'll start with the label 0, then we generate 3 choices with label 0, 3 choices with label 1, and so on. So I want to encourage like different types of samples in the batches, right? So that's one. Then next will be the choices. Again, this is not the triplet itself, but this is kind of choices. You can have 4 maybe like samples per each triplet to choose, or 5, but let's stick with 3, so at least you have the minimal number of choices, right? So for IDX in, so let me see, list the 3. So what do I need with the, oh no, I forgot one part here, sorry. So before the choices, let's have like a total main while loop, which will be len labels free. So it means as long as we have some labels free, like that are not yet so that there are at least some choices to choose from that label. So I mean, we will take out of the dataset like some letter, put it in the order for batches, then another one, and then at the end there is no samples left. That means that there is no labels free. So that's that part. You will see in the code. Hopefully it will become clear then. So if then, so we will move. Okay, let's start step by step. So there will be then the y current. So this will be the current label. From labels free, I will select IDX label, right? And then afterwards, I will go IDX label +1. Oops, so that's good. IDX label +1. I think that's fine. Okay, anyways, something is copying and working anyway. Okay, so yeah, so IDX label +1, and so I think if we can add also here, so if oh no, I know why it added another place. So above here, let's add then len labels free if the IDX label so yeah, if the label is larger or equal with that length, I want to set IDX label to 0. So I want to go in cycles, right? So I'm selecting the labels in cycles. I'm starting from the 0, going on, then again from the 0, and I'm adding this part of the code here just because after we run out of some label, we will remove the label in the bottom part of the code, and then it might be possible that we will need to go to the 0 sooner than here. So that's just one reason. Okay, let's then move here next part. So let's see, so the choices, we have actually a choices, good. So then write for IDX, so this will be then the going inside the free indexes. Again, I'm using the list here. Again, this is like nice hack of just copying the list and ensuring that if I'm removing something from the indexes free, it still works. But even though maybe I don't even need that. Yeah, I think I don't even need this part. Yeah, so that's great. Shorter code, so that's good. So that's one. Then we will select out from the dataset stuff here. There could be easier ways to do this. I mean, like, we don't need to always get out actually the image here, which we are ignoring. We could save in dataset maybe just the class indexes and then select them out. But now I'm just, okay, why it's happening like that? It should be a list object anyway. So yeah, so we're selecting out from the dataset sample by sample and getting the class index plus getting the image itself, which we are ignoring here. So then next thing is following. So for, and also just because the indexes free are shuffled, I don't know always which will be the class there. That's why I needed this. So y current equals with y. So in this case, then not for, but if, then we are finding the good choice here, right? So this is from the same class. Choices append index, I guess. Yes, and then if len choices reaches the number of choices which we like, right? That there are enough choices in our dataset, in our batch. So in this case, this will be 3 because I think I also added assert code in the top of the code that batches should be divisible by 3, but it could be something else. It could be more as well. But then you need to fix the above code where there is the assert, so that batch should divide by this number. Batch size should divide by this number of samples, right? These are the choices. So the choices are these. Then here is one part of the code where you can help me improve. Maybe there need to be some shorter way to write this. So for in choices, because I'm using the lists here, probably with numpy arrays I could do something better here. So then index is used, append, you know, like we can write just choice index, I don't know, choice index. You can write your own variable names if you want a little bit better. So I'm adding those to the index used, and then I also need to remove them from the index free, right? And this is the part which is slow. So because it needs to find that poor index, right? So if you can write this code better without the for loop, or just making that it would work faster, it would be great. If you know how to write this code faster, it would be great. So that part. So we are breaking out of the main loop there. Then in the bottom part, if len choices, so if from this particular class we don't have enough choices, so number 3, so it's not enough choices there, then we want to remove labels free from the list, so y current, right, like that. And that's about it for the code, basically. So let me actually collapse it a little bit. The last thing missing here is in the main scope that I want to store the self indexes used, right? So, and then we also need to fix, to run it to see if it works. So the reshuffle code here, right? Okay, I just don't want to scroll around, so I will copy this piece of code to the Jamboard, and then I will just run it and see if there is no bugs there. So now I'm dropping this code on the slide number 5. Hopefully, if my clipboard starts working. Okay. Slide number 5, the sampler code. Basically, it's either the sampler code or batcher code. So that is on the slide number 5. And now I'm just trying to debug, see if it works. So data loader. So let's see the data loader here. I will add the breakpoint in the main training loop. So, and it seems the code is working really nice. You see that there we have 444, 000, 333, 555, 444. And here, because I'm just using very small number of classes for debugging purposes, you can see that they are repeating in the batch, because I have batch of 66, right? But if I would add more classes, then I would not get repeating samples. So, and that's the case when I'm running this on CUDA, on GPU server, I'm just adding a lot more classes to this sample. So hopefully it's working for you as well. So I've asked in the chat, we'll scroll also back here, that there is no bugs and it's working and it's understandable. Hopefully this method of ensuring that we have choices for triplets. So he's triplet sampler code ready, plus minus. So if you type minus, then I assume that you are working still on it, but if you have some problems, then maybe you can try to copy the error messages and line numbers in the chat, because as far as I know, or maybe you can also even copy some code on the Google Classroom, because sometimes the YouTube live chat just don't allow to share links. Okay, good. Thank you. Loss. Yeah, this is correct. The error that you're getting, that is not error which is not expected, because of course, if I think everything is working for you actually, Armand, because if you're getting that error, it means that that you got so far where there is to do, which is not done, right? That's why you get that error. So I think hopefully you are all at the same page. So this is working nicely. Then we have choices. We can choose which triplets we want, right? So that is good news. So then let's make the code here to actually do the triplet loss itself. So choose the best triplets. So for, let's say so this will be very similar code to previous time, but we will combine the positive and negative part just in one loss equation. So the triplet loss is combining the both parts in one equation, so it's not even possible to divide them. You know, like you could try to do that, but basically normally it's not meant to be like that. It's always triplets, right? So here in range, so len, it's from 0 till len. Len of something, in this case, let's say len of y, y index, or let's say x, whatever. So with step 3, minus 3, so there is one caveat here. Again, the last 3 samples, right? The last 3 samples, we can mine the positive sample, but it's most likely that, it's not very convenient to mine the negative sample. It is possible that the negative sample is already included in previous samples. So that's why I'm just skipping the last 3 samples. So they will be included anyway, randomly, time to time. So if you want, you can improve the code. So here then y. By the way, let's rename y indexes. No, let's don't rename. Anyway, so y indexes I don't like that it's so long syntax, but let's keep it, because otherwise some other part of code might not work. So y, you could refactor it just with y. So that is that part, and then we use the same syntax as before, where there's a z basically you can even copy that part and check if everything is the same as I'm writing now. So Z I plus 1. So I don't want to repeat looking for pairs which I already checked. This is obvious. Like, why would you want to repeatedly check the same pairs? Used y indexes, index plus 1, like that. Then we are using some kind of distance metric. Again, let's use this case because this is L2 space. I have the L2 norm there. There is no problem using the Euclidean, which is really fast. Oh no, f pairwise distance between the, so Z I. So an expand means that I'm copying the pointers of the tensors to this shape. So the shape is Z not used. Size. There is also function repeat in the PyTorch, right? And then you, or tile. I think it was also the function tile or repeat. Or I think, really don't remember. Repeat. This is completely different approach. Then in that case we would copy the actual contents of the tensors, but expand is just the pointers. So it means that any mathematical operation with any of the instances of the pointers will be exactly to the same tensor. So distance is between those and Z not used. And then we want to have L2 or L1 distance, right? Do we want the Euclidean distance or this absolute distance, right? So that part done. Then again, the same code from the last time regarding to selecting the, again, this is the case where it could be improved. We can just select the semi-hard samples or other types of constraints, right? But again, you can even just try to find code from the last time and copy some part of it, but then at the end the loss function will be different. So d negative all samples will be d all, where y not used, it doesn't equal with y index I, so all of those samples will be negative samples. And then from the all of negative samples, j, which is the most negative sample with regards to the anchor. So our anchor is this guy. So this is the anchor. With regards to the anchor, torch argmin. So that sample, which is the closest one, which should not be there probably, but again, there is tricky stuff here. If we apply the constraint about the semi-hard like range, so with the margin, so maybe we don't want to include actually these kinds of samples. Maybe the whole triplet should be discarded. It's also possible. D negative all, and there will be dn. So this is the final distance n, which is the pair with the most negative consequences, right? D negative j, like that. And then for the debugging purposes, just for debugging purposes, I also add this distance negative, which is plus so this is just this syntax plus for the lists doesn't mean plus. So this is concat. So if list, for the list, basically list, this other list is basically the same thing as list concat other list. So in Python, this is the syntax. Again, very confusing. Seems to be mathematical syntax, but it's not mathematical syntax. So CPU and data numpy to list. Again, huge macaroni here. Don't like this, but leave it as that. So one macaroni we have here. Then for the other guy, we just copy the same stuff here, change very carefully stuff here, so not negative but positive. So positive, 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 whoops, positive, positive. Then where the classes match. So again here we could actually not do this. We could just select next two samples, right? And then use only those next two samples. This would be perfectly fine. But in the case, or in my debugging environment, and also maybe in real environment, there is a small chance that there could be more triplets, like more choices in the same of the batch. So that's why I'm still leaving this part of the code. But you could just select next two samples, right? Because in the top we are going by every tree here. So it's up to you. Like I just want to give more better options. So, and here we use argmax, which means that this is the further away sample. Again, if you apply the constraint, so if this is under the margin, then maybe we should discard this triplet at all. So that is also really important stuff. So dp, so if this basically what I mean by if this max distance, actually the distance itself, so dp, if dp is under margin, then actually we should not include this sample, or maybe if this yeah, so that you could add some constraints. So constraints means to limiting which samples we want to include in the loss function. So the positives here, pause all, pause, not used, seems to be fine. Seems to be fine. So again, the code is not so much actually. I'm trying to not give you huge amounts of code, just trying to illustrate the main idea. So losses, append. So there will be the main loss function. So we can make it in different ways. Let's use the ReLU way, right? As I say, that it can be max 0, maximum 0. It can be ReLU, so it doesn't matter. dp minus dn plus margin. Again, and here we have this really interesting triplet loss function, which is keeping the balance between the positives and negatives, keeping them apart with the margin, also ensuring that the positive clusters can be larger, like some can be larger, some can be smaller, also ensuring that all of them will always have that margin and they can move in the space. So really, I think, really nice function, and there are also, of course, some improvements to this function. So let me see, I'm adding this to the Jamboard. Again, I hope that today's session will not be super long, but will be really exciting results. So let me see, so I'm adding this to the Jamboard, slide number 6. And testing out locally. So I'm test out this part of the piece of the code locally if there is no bugs, hopefully. So the training is initiated. There will be also, so I remember, I forgot maybe to mention you, after every epoch I have small piece of code, at least, yeah, so here, that basically it reshuffles the samples after every epoch. So that's really important, I think, like, because otherwise we will have the same choices of samples every time when we run the epoch. So just before every train epoch, I'm reshuffling them and giving the model better samples to choose. So at least already we can see that really nice results. Even after the first epoch, you see that the clustering is visible quite obviously, right? That the blues are together, yellows are together, here are the blues and the reds are together. and this is just like very few number of samples. I'm literally running on a few hundred of samples on the test, right? So this is just debugging. I'm running this on CPU even. So, and I would not expect that kind of results just with classification, you know. So okay, this is epoch 2. You already see really good results, and this is like very few samples. So these kind of deep metric learning methods are much more sample efficient than any kind of classification method. So you see that this works really nice. And I'm also running this on the also on the GPU version. I will try to find, do I have some example to show from that? Okay, on the GPU version samples, so I will show that as well just in a second. Oh no, there is the train X included, which should not be included there. I will fix that in a second. The X's are actually the images, right? The images are the pictures, right? That we are actually passing to the embedding model, and I'm including those in the metrics just because I want later, just in a second, show you how to add that into the tensor board, right? So I will kill this for a moment. So let's fix the X thing here. So the metrics, this is good. Where is the images, the plot? I don't want to show in the plot X. So if the in key and not in key. Maybe I should add also here and not X, because I don't want to show the X's as well. And not X there, or, so this is really nasty code. I should improve this. Definitely should improve this X. So the way how to improve this would be, if something is in the list, so actually let me improve it. So if key in something like this, then it will be much nicer code. So do not display this, do not display this. Again, this code is not related to the loss function or whatever. So do not display this, do not test. Maybe I want to display test. Yeah, I think I want to display test. So this part. Then I'm ignoring all of this. Do I don't want to display distances, really? I want to display distances, actually. I think, I don't know. So anyway, share here and not in if key not in. So now it looks much better. So that part. We could actually also uncomment this tensor board stuff here. I will show you just in a minute also how to do that. And actually, in some of you lucky ones had the my commented code on the template, which is a little bit messy, but you had it. So tensor board this part. So I will drop these lines also in the Jamboard, and I will show you how the actual convergence for the model worked. You will see that the triplet loss converges like so much more faster than the contrastive loss. So actually I need to find some sample which is not too overfitted. Again, I did not apply some constraints. Anyway, so let me select some sample to share. So here there will be some example from the training. So there are much more classes. I don't know, like 20 classes or something. Yeah, 20 classes included here. in here. So you can see even like it's completely converged, almost like about like 20 or 30 epochs, where with the contrastive loss it was not as much stable, and it did not converge so fast. So that's one thing here. Yeah, so that is working. Hopefully it's working for you as well. So just check that few lines that I changed also works. And then we will add the last thing with regards to the tensor board, so I can show you how really nicely everything looks in the tensor board as well. So is it working so far? Is it working so far? Plus minus. Yeah, the tensor board stuff was not here. Okay, I got it. So for the tensor board writer, I actually set it that only it works when I pass the path here. Where was it? But let's change it now. Where is the tensor board? Okay, here. When I set the run path, then I do not display the plots, but I'm writing the tensor board. So instead, let's do something here. So instead, let's just move tensor board to the root here, and run path. What we could do with run path here? Okay, let's do a small hack here. Just I don't want to just actually make the whole run path stuff. Or maybe let's do it. Let's leave it as it is. Do not touch it. So just change run path to here, that there is a default value for run path is nothing. So let's add it experiment. So the results will not be displayed as a plots, but they will be saved as PNG images, and you also will have the tensor board. So I'm adding this small default value here. I will also wait for others, no worries. So I'm adding this to the slide number 8. So I added this default value of experiment. Now if I run it, then I should not get any more the error for the tensor board. I think you really like how the tensor board, this projector works. I will show you how to get the visualizations out, which are really nice. I think like I have not seen actually anything much better than tensor board projector for embeddings. If you know a better tool, then please share to me. So it seems that it works. It works. It definitely works. So just add the experiment here, then uncomment the adds colors. So I will explain that as well a little bit. I think in my courses before, I already explained how to use the tensor board. But here there is the idea that you can add to the tensor board writer all sorts of data points. Like you add the key, this will be the name of that data point, the value. You can add then which epoch step it was. You can also add not only scalars, you can add all sorts of really interesting things there. You could add audio, add figure, like the pictures, add what else you can add there, add text, add And if you add histograms, so if you actually add images, it's also really nice. For example, you add the confusion matrices, and then you have the small slider where you can see how the confusion matrices change over the epochs. So that's really nice way to visualize. I mean, like the tensor board itself for visualization is really great, but when you have like large numbers of runs, then tensor board again is not so great. There is actually additional thing that they added, which is really good direction, but do not work that well. There is a thing called add h params, which means that there is a like table where you can compare all of your runs in one place, but actually that table is still very buggy, like years later, and it still doesn't work great. But the scalars were great, the images were great, the audios were great, then also the embeddings were great. So I'll show you how to add the embeddings. So if you were the ones that got my messy template already with the embeddings added, so that will be a little bit more easier for you, but others can look up how I did this here. So first thing that's missing here actually is the images itself. So we need to add images. So to add images, we need to go to the main training loop. Here there's the losses. Where was it? I added somewhere. Okay, here. Yeah, so I actually commented out here this line, 330 line. So this should be uncommented. So we are adding to the statistics the actual images itself, the pictures. So if you would have like large face dataset, you would never ever would be able to do this. So only because we have dummy dataset we can do this. And if you had a face dataset and you still want to use projector in the tensor board, then in that case you just need to store, let's say, random 100 samples from each face, not all samples from each face. Now I'm just storing all samples from each class, which is really, it will just like fill the RAM and have problems if it's like a large dataset, right? Also, for the large datasets, we use something that's called memmap or some other memory mapping like kind of ways or databases. So this is the way how we add it here in the X. And then in the bottom part, again, those who have my messy code can experiment with that, but I will write it again myself. So there will be then following. First of all, we need the embeddings itself. So this will just come from the test dataset. So the embeddings that you will see will not be the train embeddings, which maybe are in, okay, we can actually add the train embeddings. Let's add the train embeddings. So array train embeddings just will look a little bit better. So metrics epoch, and here I want to select the train Z vectors. So these will be the embeddings of the training. Then I also want to select the X's. And I also want to select Y's, which are the class indexes. Then I want to convert the class indexes into labels. So this will be then the labels. The labels are then the dataset full labels IT for iterator in D and PY, like that, I hope. Again, very inefficient code, but still will work. Okay, so this seems good. Then tensor board writer, add embedding. Again, the image part is actually optional for the embeddings. You still can get really great embedding visualizations with tensor board, even without images. But if you add images, then it's really great. Then you will see it. So np z labels basically you will get pictures which you can show your mom, and then she'll think that you're like doing some kind of crazy AI work. Anyway, this is really funny. But anyways, you'll see it's also very useful for the actually evaluating your models. So npx global step epoch, and then we will add here some, maybe we don't even need to add tag, we could add tag train embeddings. So, but you could also add the test embeddings, you will see them as well really nicely. So then the last thing maybe would be useful is to TensorBoard flush, which means please save the actual results now. Okay, so I will copy this to the Jamboard, run it, see if there's no bugs, and then I will show you how to use it, actually, how to visualize those embeddings. So now it's running. This is added to this slide number 9. I will just generate few epochs, like maybe 2 epochs, and then show you. So on the first epoch, accuracy 89, test accuracy 93. Maybe I should run a few more, just, I don't know, like which will be the best, but still, let's run it. And next week we will look at proxy NCA loss functions, which are even, at least from the many loss functions that I studied in the deep metric learning, that's one of the my favorite ones. You will see that there are really interesting properties, and that will probably also open, at least hopefully you already are quite open-minded to see that there are many research opportunities in the deep metric learning. And that method and function probably will also give you more ideas. And then afterwards we will move to generative models, where we will apply actually the metrics. So the deep metric, the embeddings will be then used to generate new samples. That will be also really nice direction. So there are 3 epochs already done. I don't know, should I wait more? Let's just wait one more epoch, and then I will show you how to use the embeddings. Okay, let's stop it here. So then I'm pressing the terminal here. In the terminal, I just want to see what I have here is so this is not what I wanted. I'm going into session 3, the triplet loss, ls. Okay, now I have it. So there is experiment, this guy, ls experiment. Inside experiment I have tb experiment, and here I have the three runs for the TensorBoard. Okay, great. So the way how to run it is following. So you open the terminal here in the bottom part of the pie chart. Then you write inside here the TensorBoard. Then you put in 2 lines, log dir. Then you put equal sign and give the path to actual TB experiment. I really hope that this was correct. If it is correct, I will add this to the Jamboard. If not, then I will fix it. Okay, it works. Seems to be working. So in the terminal, you need to write this kind of line. I will specifically point out what you need to add there. And then you will have really nice pictures. So I'm adding this to the slide number 10, the command how to run this. And it gives you that you should open your TensorBoard in localhost 606. So let's do that. Go to the Jamboard. Let's open new slide. Open. So the TensorBoard is opening. Kind of. Maybe it likes to open in the Chrome. Let's see. I will check at least. So this is developed by Google, so maybe they like to open it only in Chrome, but we'll see. I really hope that I can open it on Safari as well. It seems not to be working on Safari. Yes, it does not work on Safari for some reason. I don't know exactly why. Anyways, so I will show you then on the other screen. So just a second. This will be fast. So first the Chrome, TensorBoard, right, like that. So here, I don't know, like why exactly. So let's start looking by this part. So smoothing, ignore scaling. Okay, cool. Now, so there's, you can see that it gives you these nice plots with all of the accuracies and the distances and the losses. So it's quite interactive. You can export them as well. So these are all scalar values. So train loss, for example, you see it goes down really nicely. You can also export it as a CSV somewhere. I don't remember exactly where, but there was an option like that. Okay, I can also put this part. Yeah, so see, like all of the metrics visible really nicely. So you can add the metrics and also filter them, right? Like test or train and see everything right at once. That's really nice way to visualize all of your data, right? So that's one. And then the projector, which is the coolest thing here, right? So let's use then the third epoch embeddings here. You see there we already have really nice clusters here of all of these letters. You can zoom in, you can drive around, like scroll around. You can also color them, so color them by the classes, right? You see really nicely. So this is PCA, Principal Component Analysis, which is, in my opinion, the most objective way to analyze the embeddings. But there are also some other ways. So this is two-dimensional, this is three-dimensional, right? Really nicely, right? Then there's also TSNA, which sometimes gives even nicer visualizations, but I would not say that this is super accurate. It's not bad. It definitely gives nicer visualizations, but like if I would want to run this model for the zero-shot setting, I would not trust it very much. Like it's trying to keep the distances the same in the new embedding space, but it still uses this kind of optimization of trying to find the best way how to plot this. And basically, we don't actually want to fit it just for visualization. We want to fit it for using in a real-life scenario. So that's why TSNA is not always the best one, but it definitely gives really nice visualizations. Then there is also uniform manifold approximation and projection. This is something new they added, I think like a year ago or something. And it's also another way how to visualize the embeddings. So yeah, so this this gives really nice insight that everything is clustered nicely. But yeah, not sure if this is the best way how to show it. And actually, you can see there is also something interesting happening there. You see that there is some blue things here. Why there are those blue things? So you see that that the number 3 here looks very similar to these 5s. At least this one. It's at least the model thinks that they are very similar to these. This one and this one and this one. Yeah, it might be. I don't know. Like this could also be mistake. You know, there are many times when you're using these kind of embedding projections, you can find very easily some mistakes where there is like mislabeling. So here again, this one, this and this looks very similar, very similar, and that's why they are. And the cool thing is that we did not actually, you know, like we just trained it on the similarity metrics. We didn't tell that they are like actually that similar. They discovered it myself, the model. So yeah, so that's it about for today. I think this is a really cool way how to visualize things, and also you understand now how to build very powerful models. For like you can now introduce in this embedding space samples that were not seen before from the same domain, and they should be also be able to cluster them. And next time, yes, let's then talk with another loss function and then move to the generative model. So that's it for today. Hopefully that was really interesting, and let's see you next